Okay, good question. Um, so ARM is an IP company, and we design the ARM computing architecture. So what that means is that we design the instruction set and all the peripherals that go around a CPU, um, and then we license that to our partners for them to put in their own silicon. We're responsible for the architecture. We design the architecture. We design implementations that use the architecture, and then others use that in their products. And the elements of the ARM architecture show up basically everywhere. Everything from the smallest embedded devices up to every enterprise server has ARM IP in it, in processors or other parts of their products. So my role at ARM, up until very recently, has been the System Ready IR architect. So that's for the IR band of the System Ready program. So that means is I'm responsible for the direction of that program. And then more recently, I have become the Lenaro CTO. Project Cassini is it's an umbrella project. It's an umbrella initiative that pulls together, it's a whole bunch of different technologies that improves how you build rich compute embedded devices. So edge devices, IoT devices. And what Cassini is aiming to do is it looks at the whole thing and it says, what are the pieces that we need? How do we get an operating system landed onto an embedded device? How do we make sure that operating system is secure? How do we make sure that the software ecosystem and all the software, particularly open source software components, fit on top and are able to land and be maintained over the lifetime of a product? Right. So this Project Cassini, it's the umbrella project that we use for all the different initiatives to make the experience of developing an ARM product, you know it's going to be secure, you know it's going to be functional, and you're able to use modern development technologies such as do cloud development and then be able to deploy it to the device. Historically, building ARM devices has been an exercise of, there's lots of great components out there, lots of very good technology, software and hardware, but putting it together into a product is a lot of work. And so what we've noted is that there's a lot of parts of building a product that are the same regardless of what product you're building. And so Project Cassini is about maturing the software components, having consistency and standards wherever we can, having common patterns for security, and programs that help us to actually prove that it is secure and that it is functional, and in large part make the experience of developing an ARM device just so much better. Certainly. I'll start with the security. And security is, it's based on the PSA, or Platform Security Architecture program. And PSA is a certification program that ARM initiated that has a process for if you have a product, and in the ARM architecture, we've got a concept of the secure world. And what it does is it's a way of evaluating and certifying that the secure world portion of the platform is meeting the requirements of the program. And it is secure, it's doing the right things with secrets, it's got the correct root of trust, it provides the appropriate interfaces to build a secure system. Right. So it is a certification, and that the silicon vendors are able to take their products and go through the PSA certification program and get a stamp at the end of it if they've met all the requirements. And then when that silicon is being put into other products, they're able to say, that those products are able to make use of the PSA guarantees. Right. So that's the security part. Security does encompass a little bit more because there are other parts to security. And there is for example, the Parsec project, which is a way of providing security functionality out to the Linux user space. But primarily, we're talking about the PSA program. Second one is standards. And this is acknowledging that historically, when you build an embedded device, it is, you create firmware, you port the firmware to the device, you port Linux to the device, you create a root file system, and generally all of these things are built into a vertically integrated stack, which is very functional, right? We're really good at that. The number of products that are out there in the market is just demonstration that this is really functional, it works well, but it's not optimal. We can do better. And so what standards does is it recognizes that there's parts of the stack where if we have a standard way of doing things, it becomes a lot easier to build product. It means that building a complete vertically integrated stack is more reliable. It also means that if you want to use components in that stack, such as a Linux distribution, Red Hat Enterprise, Red Hat, Fedora, SUSE, OpenSUSE, Leap, you are able to use those operating systems as part of your stack, and you don't have to go do something different. So we started the SystemReady program, and the SystemReady program is the natural evolution from something we did earlier called ServerReady. ServerReady was designed when we started doing ARM servers, recognized that if you can't land Windows and Enterprise Linux on the device, then you don't have a product, right? So standards are absolutely required. But in looking at the standards that we chose and the way that it works, realized, you know what, this can be expanded. And if we take the UEFI ABI and apply it to other parts of the ARM ecosystem, that we can actually make those parts of the ecosystem better as well. And so that's what the SystemReady program is. SystemReady takes ServerReady and expands it. And the particularly for embedded, there's some unique characteristics that we have to deal with. In embedded edge IoT devices, usually UEFI is implemented with the EDK2 project or a commercial BIOS. Most of those platforms use ACPI. But in embedded Linux, we don't do any of that. We use U-boot and we use device tree. So what we did with SystemReady is for that embedded and edge use cases, we said, we're going to use the software that's already really mature and has a great community behind it, but we're going to choose standards that work there. So we standardized still on the UEFI ABI, but made sure to tailored for being able to implement UEFI in U-boot. Right? So U-boot has been gaining the UEFI ABI for quite a few years now. And what SystemReady does is it takes that and uses that as the baseline standard, which means we can use the same technology for booting distros across all bands of SystemReady, across all ARM platforms. And then the other thing we do is we standardize on device tree. Linux is perfectly happy to take either ACPI or device tree, but device tree is what is used in embedded. So that's what we've standardized on. And this gives us a common platform. So that leads to the SystemReady program, which I'll talk about a little bit more, but that's a certification program that guarantees things work properly there. And then finally, the third part of Cassini is that developer experience. And this is not about certification. This is not about creating programs that you have to implement specific things. This is about encouraging and developing a software ecosystem that is integrated, where we can have multiple companies that have their own products. We can have multiple open source projects. We can have multiple applications that you can develop in. You can do cloud native development. You can deploy it out to the platform, and it's all those layers of the stack that are required to have that to have that ecosystem. What it means is we wanted a way to identify products that are going to be compatible with each other or have a much higher likelihood of being compatible than otherwise. And so with the certification program, what it means in this case is that a given product is submitted for testing, And we have a test suite and we have a set of requirements that are run through that the platform must meet. And it's not just that they must say that you meet them. We actually test it. Actually must confirm that it meets it. So we have the standard, and again, I'm speaking specifically about System Ready IR, and I know we're going to talk about that. We'll come and talk about the different bands in a moment. But we have standards that the platform has to be built against. We actually test it. We have an ACS test suite. It has to boot real operating systems that are controlled by a third party. And if the platform gets through all of those hoops, if it can check all of those boxes and be tested, confirmed to meet the requirements, then we issue a certificate. And we say, this platform is certified as System Ready compliant. And we have this, being a certification program, we have multiple different parts of the ARM ecosystem, from server all the way down to edge and embedded, where we're able to do this program. This is integrated. So it is, if you think about a PC market, this would be the equivalent of the hardware and the firmware, right? And it is for this part of standards, and as I said, there's other places where standards make sense, but for the Cassini program, we are focusing on the platform standards. And so this is creating that separation between hardware and firmware at the bottom, and then the operating systems that run on it at the top. And so this certification program is all about that stack, that integrated firmware and hardware that allow you to run OSs and applications. There are lots of benefits. So there's the integration, there's consistency, right? It means even if you're building a vertically integrated product where all the components are still one binary, by having this well-defined interface, it means you don't have per platform differences that you've got to adapt to. It makes it feasible to do a single OS, even if you've got, let's say you've got a fleet of devices that you're going to deploy. It means that you can have one operating system image that supports all of them. It encourages interoperability, right? So this means that one company doesn't need to be in charge of the entire device. It gives opportunities for having a company that is particularly good at, say, maintenance and deployment to maintain the physical product that might be owned by another product. It allows the ODMs to not have to do as much work to support their firmware, or when an OEM actually picks it up and puts it into a product, because there's consistency. And I mean, what I like to talk about, it allows people to do crazy things. Standardization is one of those weird things that if you do it right, it enables the crazy. And I love enabling the crazy, because that's the creativity. That's the doing something different that no one else thought of. And the reason it enables that is that instead of dealing with the mundane, how do you get the software running? You get to focus on what's actually interesting, right? And so standardization, we've got, when I'm doing presentations, or ARM does presentations about this, we've got this great graphic which shows a seesaw. And we've got extreme standardization on one side and basically Wild West on the other. And right in the middle, we identify that as enabling innovation, right? So the standards are the appropriate level of standards that allows you to not do work on the common stuff, and then just go and focus on all the crazy innovation that you want to do. So as I mentioned, System Ready evolved out of the Server Ready program. And Server Ready was specifically focused on ARM enterprise servers. So this is high performance CPUs that were going to be put into data center running data center workloads. And we knew we needed the standards because we needed the OSs on top. That set of standards makes all kinds of sense in enterprise servers, but it doesn't make any sense when you start looking at lower power profile devices, or other types of devices that are out there. So the Server Ready program became the System Ready SR program. And then the next two bands that we defined, and this was very much looking at what do our partners need, right? This is a very pragmatic program of it's being driven by what our partners need. And so then there was the ES program. And the ES program is very similar to the SystemReady SR in terms of the software ecosystem. So we're still looking at being able to run enterprise Linux. We're still looking at being able to run Windows. I say we're looking at, no, we are able to. We're able to run Windows. We're able to run ESXi from VMware. We're able to run enterprise Linux. But the hardware, the targets that want to run that are the embedded A-class silicon that doesn't meet the hardware standards, doesn't meet the high performance requirements that you need in the server space, right? In the server space, we push things and we push new architecture features. We're really looking for performance there. But those features don't always appear in the embedded SoCs. So the ES band is using the same UEFI and ACPI baseline, able to run the same OSs, but the hardware spec is expected to be kind of the embedded server device, right? So this might be, examples might be a NAS box or edge compute boxes that are deployed in the field. So that's the ES band, right? So SR and ES actually look very similar, but the hardware profile is different. And then finally, the IR band. And what was realized when we started doing this is the embedded ecosystem is different, which I already talked about. And because it's different, we need a different approach. So we used the same standards where it made sense, hence UEFI. We used device tree for the system description because that is what is predominantly, that's what's working now. And we wanted a program that could be adopted immediately without causing massive change in the embedded ecosystem. And from pragmatic speaking, if we try to do massive change, it's just not going to happen and no one's going to care. But we also made sure that regardless of SR, ES, and IR, that Linux was going to be able to run across all of them. And so because Linux equally will accept ACPI or device tree in the same kernel image, we're talking about we can do this the whole across the band, right? So SR and ES are focused on multiple operating systems. IR is primarily focused on embedded Linux and that large ecosystem of devices that are there. And then there's finally the new band, which is LS, and that one is still being defined. And this is for the hyperscalers, the cloud service providers who want to use a Linux boot firmware ecosystem. And so there's a new set of requirements that's specifically around what it looks like when we've got Linux boot as the firmware on the platform. And in all cases, we have the same criteria. We put standards out there on what the platform must do. We create a test suite that tests it, and any platform that has a SystemReady brand, has a SystemReady certificate, has been tested. We know that it meets the requirements. Okay, so first of all, there's no way that we would have been able to do this if it wasn't for the ecosystem of developers. So we've got Lenaro in particular has done an awful lot of work within their Ledge group. And within their, and of the silicon vendors, we've got NXP and SocioNext and others who have been contributing to U-Boot, to ARM trusted firmware, to Opti that enables the features that we need. So the kinds of ecosystems we're talking about, first of all, there's the silicon vendors, where they're seeing the value of, if they've got the standardization, it's easier to get their products out to the market. And that is true whether you're talking enterprise server or embedded server or edge device. It's true across the board. We've got the ecosystem of the product developers, ODM, so board vendors, they're putting the silicon on there. Oftentimes their focus is not developing firmware features. So they want to be able to, they want to be able to reduce the amount of engineering that they have to do to get into new markets. There is, now I'll speak specifically about the Linux community, or embedded Linux community right now. there is a very rich ecosystem community of developers who work on embedded Linux, who are active in contributing to the upstream kernel and contributing to U-boot, who have gotten very, very good at building products. It would be unfair to say, actually it would be flat out wrong to say the embedded Linux ecosystem was failing and we came along with something that fixed it, right? It's not even close to that. This is a very robust, very vibrant ecosystem, active developers. And what this program does is it actually comes along and it says, great, here's a way that we can do things better. And it's actually in working with that community that we've created this the program. So in SystemReady IR, for example, the standard is Embedded Base Boot Requirements, EBBR. And you can find EBBR on GitHub. That spec is developed completely in the open as an open source project, CC by SA licensed. And it is embedded Linux developers who are participating in creating that standard. And then that's what we base the SystemReady program on. Very much, very much. It is certainly from SystemReady. SystemReady itself is certainly an ARM initiative, but the way that we're trying to do this is with the community. We're not creating new stuff. We're working with what's existing. And the way that we're running it is rather than ARM taking all of this testing in-house, we are working with third-party testing houses so that product vendors are able to get their devices to the test house to go through all the testing, and it's not something that's all just internal to ARM. In practical terms, it means that they have something that they can aim at as a base set of requirements when they're building their development kit, when they're building their software development kit and their reference platforms. And it means that there are more operating systems that they can demonstrate on their platforms and then support once they've landed onto real products. Yeah, it gives them a common interface. It expands what they're able to access in terms of the market. Here's a concrete example. If I'm a silicon vendor and I put out an SDK that's based on Yocto and I'm able to build a Yocto image, I now have to maintain that Yocto image and keep up to date with the latest Yocto. I need to make sure U-boot's not broken. That's all that I'm demonstrating. That's all I can provide. If instead I build a base, and sure, I'm still using Yocto, but I'm building a base that can actually go through SystemReady certification. It means that I can demonstrate that Yocto, I can do everything I did before, but I can also run a Red Hat, SUSE, Ubuntu, Debian image on the platform. It means that I've got access to a larger software ecosystem. There's two classes of how these things get into the market. In one case, you have a single vendor who builds their hardware and they put the software on top, and that's the product. But there's quite a large ecosystem as well of ODMs and OEMs, where the ODMs build the actual hardware targets, and the OEMs are the ones who are adopting those and putting the application on and creating the final product. In the ODM-OEM model, this is huge, because now the OEMs are able to say to their ODMs, look, we want SystemReady. Be SystemReady compliant, and then we're potentially a customer because we can use your product. The ODMs, similarly, it's something that they can put on their product sheet of, we are SystemReady compliant. You're not going to need to go and do software porting to get Linux up and running on this board. In the case of vertically integrated, the argument is not as strong because there's not that certification need, and the vendor would own all the pieces. However, I mean, in practical terms, building an embedded product is actually pretty easy. Maintaining that product over time is a pain in the backside. So one of the things that this allows you to do with System Ready is because it's a common interface, it means you're using, once you get more products, you're actually using the same interfaces across the board. It means you've got the opportunity of doing, or it's easier to do single images across multiple targets. It reduces the amount of thinking you have to do or custom engineering just to get up and running. It means you don't have to roll your own update solution. That's one of the things we just realized was important, is that in the embedded devices, we have to have a way to update firmware. And so that's baked in. That's a requirement. Software developers, it means you're not tied to a particular OS. You're able to do Yocto, you're able to do a distro, or if you need to do bare metal, you can do that too. And in fact, it gives you a set of functionalities and APIs that wouldn't be there otherwise. It also means that you're going to get more support from your vendor, because the vendor, in producing a System Ready compliant product, it means that what they produce as firmware, as binaries, can actually be deployed. It's not merely a reference that you get the board, you throw it away, and you build your own firmware. Or for all four bands, we've started from the point of view of we're going to start with a baseline and going to build over time. That is particularly visible in the IR band because we have a software ecosystem that didn't have any standards. And the goal of System Ready IR is to work with that ecosystem to bring the expected level of standards along and build it up. So this first ready of System Ready IR, you will see the UEFI ABI, you will see an update interface, and you will see being able to boot some OSs. We're planning to do a System Ready IR 2.0 this year. And the goals of that one is going to bring in schema testing on the device tree, more compatibility and integration with FWFD for the firmware update. And one of the things that I really want to do, and I probably can't make it required this year, but it's on the roadmap, is make secure boot mandatory. So that functionality, being able to enroll the platform key, have a secure platform, and test it and confirm that it's actually secure. Because that's what's needed in embedded devices. And so the goal of System Ready is we're going to extend this over time, and we're going to increase the requirements in pace with the community, in pace with the ecosystem. We're not going to require things that can't be done, but we're also going to push a little bit and push the envelope to what is valuable and needed for the ecosystem. I've talked mostly about the firmware aspects, but there's also hardware aspects of interfaces and the way that the IP blocks are configured that is important for operating system compatibility. And so one of the standards that feeds into System Ready is called BSA, or Base System Architecture. And what the base system architecture defines is how the CPU core is configured, the features that must be there, and the IP blocks that are around the CPU and what are required. The trouble that we've run into, though, is it's really hard, using the software-only approach, it's really hard to test the compatibility of the hardware before the silicon is actually available. And we found, there's particular problems. The two big problems that we run into is if a lot of silicon implements different kinds of UARTs, which don't match what BSA requires. And then the really big one is almost every PCIe host controller has a quirk that isn't quite right. And so we've realized, we need a way to test these things before the silicon actually gets taped out. And so that led to we've now got a System Ready pre-silicon program where we're working with Synopsys and Cadence and others so that there are test benches and able to run through System Ready testing before the design actually gets taped out. And this will prove out all those interfaces to make sure that we don't run into a situation where silicon's out there, it's not quite compliant, and we have to issue a waiver because the silicon's not going to be respun. The goal here, of course, is we want the operating systems to run without having to have special software changes to support custom or support odd behavior of the silicon. Instead, if we've got pre-silicon testing and all the interfaces are there, the OSs should just work.